I am Chris Williams, Astrophysics Chris, until my astrophysics exams are held in October. And as a means of revising and also to develop my Asperger syndrome communication skills, I'm going to communicate to the YouTube audience my revision notes. Also, this will build my confidence on the subjects I need to know about, and I will be communicating astrophysics to you. So if you are interested in astrophysics, if you don't study it yourself, then I will be educating you. So I've got my notes on my computer screen. This is obviously going to be one big disaster. This is the second time I've done this, but I'm not doing it for you. I'm doing it for me. So let's get on with this. Right. The topic I'm going to be talking about today are sub-millimeter galaxies and something called the K correction. Right, essentially, when you're observing a galaxy in the sub-millimeter wavelength spectrum from ground-based telescopes or from satellites orbiting the Earth, you obviously have to consider that the object that you're imaging is a very long way away. So you're in the observed frame of reference, and the object itself is in the so-called rest frame. And according to my notes, the flux, the energy that's been emitted by the object that's been observed, what you observe the energy to be is not its genuine emitted energy, and indeed it will come across as brighter than what it really is, and this is the so-called K correction. At sub-millimeter wavelengths and also at millimeter wavelengths as well, galaxy spectra are dominated by the steep Rayleigh-Johns slope, and this essentially means that there's a lot of dust in the universe, as I'm sure you can appreciate, particularly in the galaxy, and that this dust can emit thermal radiation, and that leads to this perceived increase in flux and also brighter luminosity as well. Obviously, I'm being a bit dodgy with the terms. I just said flux and I said luminosity. You might want to poke me and say, what is flux and what is luminosity? Well, let's not get too bogged down in that. Clearly, in the exam, I'm not going to be speaking the knowledge. I'm going to be writing the knowledge, but here I'm talking through the knowledge, so I can say, yes, I understand where this is going. Of course, if there are any gaps, I can fill them in at a later time myself. Right, so this K correction, where the object that is far away seems brighter due to thermal dust emissions. The K correction is extremely strong and can make a more distant galaxy brighter than a close identical galaxy. That's what I just said. The first camera to operate at sub-millimeter or millimeter wavelengths, making use of this K correction, was SCUBA, which is the sub-millimeter common user barometer array. Sub-millimeter wave imaging has the benefit of negative K corrections, but imaging at other wavelengths does not. The positions of sub-millimeter galaxies are typically only accurate a few arc seconds, but within this area can be many optical galaxies, and indeed this is explained by a picture that I saw where you've got what appears to be a bright source of light. Of course, zoom in on that, it turns out that there are many small galaxies very far away in the universe. Because when it's unresolved, it's one point of intense luminosity, but it turns out it's loads of very faint galaxies. Right, then we're on to ultra deep radio mapping, and this is managed to detect around half of the sub-millimeter galaxies, but the rest were unidentified in even the deepest 1.4 gigahertz images of the sky, and this will improve when the Atacama Large Millimeter Array begins operations, which I think is going to be in 2012. Some extremely red objects appear to be dusty starbursts, where star formation is happening, where there's clearly a lot of dust present during the star formation. It turns out that approximately 10 to 20% of the submillimeter galaxies are actually extremely red objects. An early indication of a similar fraction appeared to be BZK starbursts, but my notes don't go into what BZK starbursts is. There's a considerable variety of definitions of various types of red galaxies, and there's often overlap in membership, such as distant red galaxies and dust obscured galaxies. Distant red galaxies and BZK galaxies contribute tens of percent to the cosmic submillimeter background light, so 10% each, I assume that means. The key thing I'm trying to emphasize here, I'm trying to take away from these particular parts of the notes, is that there is this K correction, whereby galaxies which are far away may seem brighter than what they really are because of thermal radiation from dust in their area, and this then leads to us finding that 10% of these objects are detected in the submeter wave imaging. 10% of them are extremely red objects associated with star formation, and also very, very bright sources when resolved turn out to be a cluster of very young galaxies at extremely large redshifts, very far away from the Earth. Ultraluminous and hyperluminous infrared galaxies is next in the notes. The IRAS satellite mapped 98% of the sky at 4 different micrometer wavelengths and found many tens of thousands of star-forming galaxies. And it turns out that many galaxies had 10 to the power 12 solar luminosities, which is 1 or 2 orders of magnitude more luminous than the Milky Way. It was not immediately clear what caused these high luminosities, but violent starbursts were suspected. The breakdown here of some luminosities: luminous infrared galaxies 10 to the power 12 solar luminosities, ultraluminous infrared galaxies 10 to the 13 solar luminosities, and hyperluminous infrared galaxies greater than 10 to the 13. And in the local universe, the ultraluminous infrared galaxies contribute a negligible amount to the star formation density, but the discovery of submillimeter galaxies and surveys by the Spitzer Space Telescope have demonstrated that the fractional contributions from ultraluminous to the cosmic star formation history increases strongly with redshift. So it's fair to say that the greater the redshift, the greater the population of ultraluminous infrared galaxies, 10 to the 13 solar luminosities. So clearly this indicates that I was talking a few moments ago about submillimeter, but with infrared you can go back to even further redshifts in your pursuit of very faint galaxies which cannot be detected optically, but with the small wavelength radiation. That's not what I meant to say. But what I'm saying is, when you're applying smaller wavelength surveys like submillimeter, because of the differences in temperatures, you then detect objects which you would not necessarily see at the other end of the spectrum. So a source might be a stronger emitter in the submillimeter wavelengths rather than in the gamma wavelengths, for example. Right, and in my third episode, where I hope that my confidence will improve and where I'll be a more coherent communicator, I will be talking about measuring star formation rates. So I hope that my coherence on this will improve, and even if it doesn't, visit musings.chriswims.blogspot.com, where I will be writing down in words what I am trying to talk about here. As I say, I'm trying to revise for exams. I'm trying to develop my communication ability to communicate this knowledge, which is going to be important for the exams.